And maybe our theories are a very good approximation to nature, but we all expect that ultimately we will have to revise them. Science is inherently is inherently built on skepticism. And we have learned that in order for science to succeed, we must have openness. Scientific findings must be available to all, and we must, if we're to be successful, allow anyone to contribute to the advancement of science. It's for that reason that a healthy scientific culture requires an open society. And science itself and the pursuit of science promotes tolerance. To be successful in science, we must allow people with different points of view to air their ideas, because often they are right and the establishment of science is wrong. So we have learned to construct a scientific culture which is open and tolerant. It's for that reason, perhaps, that scientists often play a large role in promoting democracy. It's no surprise that in the Soviet Union, one of the leaders of the move towards democracy was Andrei Sakharov, a leading theoretical physicist. Science promotes democracy. It requires an open and tolerant society with free expression of thought. Well, let me turn to the main product of science, knowledge. We pursue science to learn the secrets of nature, to answer all the why questions that children ask. Why is the sky blue? Where did I come from? I will discuss briefly the contributions, the history of science over the short time we've been doing it. In my field, the queen of science, physics, astrophysics, and cosmology, where we have, in the last century, totally revolutionized our understanding of the universe, and finally, in biology, where we are making enormous strides. So I'll start with physics, where over the last 400 years, physics is the oldest of the modern sciences, we have discovered the basic laws of motion and the symmetries that underlie all physical phenomena. Physics is basic because, in the end, it's all physics. In the last century, we have confirmed Democritus' idea that the underlying structure of matter is made out of atoms, point-like objects which interact according to laws we understand. And then we discovered that within atoms, reality is very different and very strange and governed by quantum laws, quantum mechanics. And towards the end of the last century, we finally constructed what is called the Standard Model, a comprehensive theory of the forces that act within the atom and within the nucleus. We identified the basic constituents of matter and are today striving to push forward and unite all the forces of nature. It all started with Galileo, who was really the first to apply the scientific method to the study of ordinary bodies in motion, and learned that the language of physics is mathematics, that the regularities that we discover in nature can be summarized and modeled by beautiful mathematical constructions, and those mathematical constructions can be then used to predict and calculate the behavior of physical phenomena with exquisite precision. And Galileo was followed by Newton, who of course realized that the laws of physics govern the same laws of physics. The law of gravity, which he discovered, govern both the motion of the planets and the apples. That the laws of nature have a universal character to them. They work everywhere in the visible universe. and explain, as we learn more and more, all phenomena that we can observe. In the 19th century, the two big advances were the understanding of one other of the basic forces of nature, the force of electricity, uniting that with the force of magnetism, and understanding that light itself, radiation, light is simply a wave of an electromagnetic field that transmits the electric and magnetic forces. And Maxwell united electricity and magnetism in a theory, the first of our unified theories, with beautiful equations that could be put on one t-shirt, and explain all the electrical and magnetic phenomena that we are now so accustomed to and which generated much of the Industrial Revolution. Later in the century, Ernst Boltzmann and many others figured out the laws of heat and energy and thermodynamics, how large collections of atoms act in a constructive way, and he understood the basic law of entropy. And finally, in the 20th century, we truly developed an atomic theory and confirmed that all matter is made out of atoms whose structure we deduced. And a whole collection of people pictured here, some of whom you might recognize, discovered and understood how these atoms are in fact made out of electrons circulating a very small nucleus and are governed by strange probabilistic laws of quantum mechanics. And armed with that theoretical understanding, the quantum mechanical nature of the electrical forces that work inside the atom, we have over this last century been able to start accounting via the collective behavior of atoms for all the properties and phases of matter. We truly are in a position and gaining more and more understanding of how, when you put atoms together, all of the properties of ordinary material, of the chemical reactions, of biochemistry, and therefore biology, emerge from the collective behavior of these atoms. And towards the, well, we also learned that Newton's theory had to be slightly revised. Einstein's taught us that space and time is dynamical, and its curvature gives rise to gravity. This is a great example of the replacement of Newton's theory of gravity with a better theory, not the overthrow of Newton, because Newton's theory is still extraordinarily accurate except in unusual cases. But still, Einstein's theory is right. Newton's theory is only a good, wrong approximation. And finally, towards the end of the 20th century, we completed what is now called the Standard Model of Particle Interactions, a comprehensive theory of the basic constituents of matter, quarks that make up the nucleus, and leptons like the electron that circulate in atoms, three families of such matter particles, and the complete understanding of the forces that act within the atom, electricity and magnetism, and within the nucleus, the two kinds of force that act in the nucleus, the weak and the strong. Now, since my work had something to do with the strong nuclear force, I'll tell you very briefly what we did that led to the understanding of the strong nuclear force, which was a big mystery even towards the, even until the 1970s, because the nucleus is such a small object and so hard to probe. And it was only by the middle of the 20th century that people were able to look inside the nucleus with particle accelerators and to determine that it looked very much like within the nucleus at the center of atoms, the nucleons, the protons that make up the nuclei of atoms, looked as if in certain experiments they were made out of freely moving quarks, strange particles with weird properties that nobody had ever seen freely moving in space. And most people didn't believe that they existed for that reason. There was no way of pulling them out of the proton, yet the experiments showed that the proton looked as if it was made of quarks. And how could that be? And that's what we understood in the end. And it all has to do with the strange properties of the vacuum. Now you might think the vacuum is a pretty boring thing. Now this is your picture perhaps of the vacuum, this white sheet of paper. If you were to remove everything from this room, all the people and all the air, there'd be nothing left, and you would cool it to absolute zero, you'd be left with a vacuum, nothing, and that's what nothing looks like, but that's wrong. The classical vacuum is empty, but in quantum mechanics, this new strange way of looking at the world, where we have this uncertainty principle operating, this cannot be the picture of the vacuum, because to test that, to observe the vacuum, you would have to probe it, and when you probe it, you set it in motion. The vacuum has in it fields, like the field of electricity and electromagnetic field, and other fields, the quantum chromodynamic field of the strong nuclear force, and you excite those fields when you probe the vacuum, so therefore they must always be excited, have some motion. We call that zero-point motion. I can actually show you what the vacuum really looks like based on our very successful theory. We can calculate and simulate and draw and have a movie of what the vacuum looks like. This is the vacuum in nature, as when it's viewed at scales, nuclear scales. So this here is the size of 10 to the minus 13 centimeters, the size of a proton, the nucleus of hydrogen. So this is a very short distance here, but on those distance scale, the vacuum is full of these fluctuating fields. You don't see that when you look with your eyes, because it's all blurred out and it looks like that white sheet of paper. But this is what's going on. The vacuum is a complicated place. And when you put quarks in that vacuum, this complicated medium, you could understand how the properties of the vacuum are such that when the quarks are close together, the force is weak, and yet when you pull them apart, the force becomes strong. That's what we call asymptotic freedom, and we found the theory that does that, quantum chromodynamics, and that's why you can't pull